Carlos Santana. Hello, today's topic is about neutralization reactions. So we have been studying acids on their own, bases on their own, but today we start putting them at the same time in the same container and see what happens. So today's topic will be neutralization and also a little bit about pH curves, whatever those are. And this is, even though we are in topics reactivity 3.1.7 and 3.1.8, we will also do small crossover with the reactivity 2.1.2 because we will be using reaction equations to find out, well, the amount of base or acid depending on the neutralization reaction. But let's start. Alrighty, so today's goal is to see that pH curve in the very end. Then we will see, before that we will see how the salts are formed, and there is a bunch of different kind of reactions that you should know in general. If you have acid plus metal, what do you get out from it? If you have acid plus carbonate, what do you get out from it? So in general, neutralization reaction, what that is, there you have base reacting with acid, and what do we get? In general, you always get water if there is hydroxyl group in the base. The hydroxyl group from the base reacts with the proton from the acid and they form the water. And everything else that you have after that, here we have sodium ion, here we have chloride ion. Those ions, they form salt. And remember, when salt is being formed, it must be neutral, so it can't have total charge of +1 or -3 or anything like that. So let's keep that in mind. And that is basically this general equation number 2, but also these general equations. What do you get if you add acid into metal, metal into acid? Well, you get salt, but you also get hydrogen gas. If you add carbonate into acid, you get salt, you get water, but you also get carbon dioxide. So understanding how the salt is being formed, it is important because we need it in all of these. But the idea is always the same. You form this something else, and then what you have left, you form the salt. Okay, let's see the acid plus metal. So we get salt and hydrogen gas. This doesn't apply for all the metals. Why? We will see that later in the next year. So now it is enough to understand that this works for metals from the first main group and the second main group. And well, a bunch of other metals. Here is some example reactions. So here is zinc reacting with hydrochloric acid. Okay, what do we get? We remember this rule, acid plus metal, we get salt and hydrogen gas. So let's first form the hydrogen gas out from the hydrogen. Well, we need 2 of those hydrochloric acid molecules because in one hydrogen molecule there's 2 hydrogens. And then what we have left? We have zinc, we have chloride ions, they form the salt, and we get zinc chloride. And the zinc usually has the charge of 2+, and that is something that you should know already at this point. Then if we have sulfuric acid plus iron, well, again, there comes the hydrogen gas out from the acid's hydrogens. Then what we have left, we have iron, we have sulfate, so there comes the iron sulfate. And here is magnesium reacting with ethanoic acid, and the same story goes on and on and on. So what metals? Metals from the group 1, metals from the group 2, but then there is also metals such as zinc and iron. There is some ruling in this, but you will see it later. So don't worry if you don't get it yet. It is enough to understand that, for example, zinc and iron and the metals from group 1, they are the ones when they react with acid, you get hydrogen gas and the salt. Okay, so now to the case where we have acid and a base reacting, and we get salt and water. These reactions produce the water always if these reactions happen in aqueous solutions. So if I have aqueous solution of acid, if I have aqueous solution of base, then I will always get the salt and water. But notice that these acid plus base reactions can happen so that the water is not being formed. This was the example that we saw when we started studying theory. There we had ammonium reacting with hydrochloric acid. The acid gives the proton to base. We get ammonium ion, and the ammonium ion then, well, forms a salt with the chloride ion, and boom, we get ammonium chloride. So there we get only the salt, but not water. So my memory rule is that whenever the base contains the hydroxyl group, then it will form water. But in the case of aqueous solutions, you will always be getting out water. Let's see a few examples. This is something that we have already seen billions of times. Here we have nitric acid reacting with ammonium hydroxide. Okay, we notice acid plus base in aqueous solution. It means that we will be getting out water and then salt. The water is made out from the hydroxide ion, from the base, and from the proton that comes from the acid. So now we have just made the water molecule. Then what we have left? We have ammonium ion over here. We have nitrate ion over here. You combine them and you get ammonium nitrate. And you get the salt out. Well, something else about the neutralization reactions is that they eventually happen between the protons and the hydroxide ions. God damn, this is a mess! The protons, they are positively charged. The hydroxide ions, they are negatively charged. So when they react, that reaction will be exothermic. So the enthalpy change will always be less than 0. How to remember that is that, well, this is positively charged particle. This is negatively charged particle. There will be attraction between those particles. So it will be releasing energy. So the enthalpy change will be negative. That is how I remember this, that these reactions are always exothermic. If we mix acid and a base, the reaction is exothermic, so we should see that the solution's temperature increases. So when we do all of these reactions in aqueous solutions, we should see that the temperature of the solution increases. And it can increase so much that the solution starts to boil. Then, acid plus carbonate. What do we get? We get water, and we get carbon dioxide, and then the salt. And these reactions are the ones that you see somebody adds white powder, usually baking soda or some other carbonate into acid, and you see lots of bubbles and hissing and stuff like that. That is caused by the carbon dioxide that is being released here. What is the source of the carbon dioxide? Well, it doesn't come from the acid, it comes from the carbonate. All these carbonates, they contain carbonate ion, CO3 minus. And if you take a look at these, you can easily see that you can generate carbon dioxide molecule out from these ions pretty easily. So that is how we form this carbon dioxide molecule. Then we get the water out. So how that water is being made, there isn't so easy rules like hydroxide ion plus proton, you get it. What I recommend is that you remember that water comes out from this reaction. So when you remember that, if you take a look at the acid will give away the protons, so you will have eventually the negative ion left. Check. And the carbonate, well, it contains a positive ion and it contains negative ion, the carbonate. If the carbonate is the source of the carbon dioxide, well, we will get rid of the carbon from there, and the positive ion that is being left here is the one that will form the salt. So that is my only help for you how to form the salt. So the negative ion from the acid and the positive ion from the carbonate, they form the salt here. Here is sulfuric acid reacting with sodium carbonate. So again, acid plus carbonate, some bells should be ringing. The carbonate ion will form carbon dioxide, check. When we have used these protons here and formed water some hideous way, what we have left? We have left negative ion from the carbonate, we have the positive ion, and these two will form the sodium sulfate, the salt. When we are describing these reactions, the IB would love that you would use this term, effervescence, and it means that there will be lots of gas, lots of bubbles, and lots of fizzing sound. But this is a concept that you should know, effervescence. Now, work with these exercises for a brief moment, then continue watching this video. These are from the topic reactivity 3.1.8, and now when you are writing these, well, for example, neutralization reactions, all of these exercises should be done without the help of internet or course book. You should know what is the formula of phosphoric acid or potassium hydroxide or ammonium chloride or potassium methanoate. You should be able to generate all of these on your own. One common thing that we do with acids and bases is titration. And that is a method which we have used once to find out the concentration of acid that, well, was unknown. So here is a small picture of the setup. So what we have here is we have burette, and that contains solution, and we know from that solution its concentration, we know the volume because probably we have been making that solution. And if you remember the concentrations formula, from the concentrations formula you can solve that the amount of substance is the concentration times volume. So when we use this liquid here from the burette, we can always calculate how many moles we have used that. And in the bottom here we have our mysterious sample. The only thing we know from that sample is that it is some acid, some base, and we have taken a fixed volume of that. So we know only the volume of that solution. But the concentration is something that we don't know. But when we know the reaction equation between this substance and this substance, we can take a look at the reaction equation. We can find out from the coefficients the amount of substance of this here. And then we can use the regular concentrations formula, N divided by volume. And haha, we get the concentration. Okay, now we start calling the point at which the neutralization has happened perfectly. So reactants, they have depleted one another. We call that point as equivalence point. And that is really, really important concept. So equivalence point means that the substances have neutralized one another completely. How we can see that? We can use indicator here that changes color. We have done that in the first period, but also that can be done with the pH probe. And we will be practicing how to do that later in the IB. For example, if we have vinegar is substance that contains ethanoic acid. If we have vinegar and we want to find out the concentration of ethanoic acid in there, what we could do is that we prepare, for example, sodium hydroxide. When we prepare it, we know what is the concentration of that. We know, well, that it's sodium hydroxide. And then we do the titration so that we have sodium hydroxide up here in the burette. We take ethanoic acid, we take the vinegar, some kind of volume sample, and then we do the titration with indicator, for example, phenolphthalein. When the color changes, then we stop the titration. We can read the volume of consumed sodium hydroxide. Then we can solve the amount of sodium hydroxide used. Then from the reaction equation, we can find out the amount of acid we used. And then we can find out the concentration with the formula C is N divided by V. One thing that we should always do in these neutralization titrations is to take a look at the reaction equation that is occurring over there. And the skill to read from the reaction equation's coefficients how many moles we need that to so that the other one reacts completely, etc. That skill here is again really, really important. In the case of hydrochloric acid and sodium hydroxide titration, we get water and salt. We knew that already. In this reaction equation, we see that the coefficients are 1 and 1. So we see that the amount of hydrochloric acid equals the amount of sodium hydroxide. Sometimes it is like that, but sometimes it is a little bit more difficult. If we have hydrochloric acid reacting with barium hydroxide, when the reaction equation is balanced, it will look like this. 2 hydrochloric acid molecules, 1 barium hydroxide molecule. We get 2 waters and barium chloride. When this reaction happens, basically 1 barium hydroxide molecule consumes 2 hydrochloric acid molecules. So when we are doing that trick, okay, let's find out the amount of barium hydroxide there. If we know the amount of hydrochloric acid, then it is always 2 times the amount of hydrochloric acid in moles. Write always the reaction equation for the neutralization reaction when you are doing the titration. You will be needing that. To find out the equivalence point, we will be using indicator or we do that pH curve. I don't know that thing, we haven't learned yet. What is the pH indicator that we will be, the acid-base indicator that we will be using? In the data booklet, there is a table that contains information of some indicators. Table 18, acid-base indicators. Here is list of different kind of indicators, such as methyl orange. There is some Elvish language pKa here. I don't know what that means. pH range, color change, acid, alkali. So how to read this if you are picking up indicator for your neutralization titration? If you know that the neutralization's pH will be close to, for example, 4.7, then it means that you should pick an indicator which has the pKa value remotely close to that. So now, in the case of that, it would be bromocresol green. The pH range where the color change occurs is between 4 and 5.6. So when the pH is 4 or less than that, the color will be yellowish. When the pH is 5.6 or greater, the color will be blue or bluish. The second way to find out the equivalence point, the point at which the acid and a base have neutralized one another, is to plot pH curve. And notice, standard level students need to only know how to read pH curve of strong acid and a strong base. Higher level students, on the other hand, oh boy, we will do many of these curves later in the second year of IB. What has happened here? In this example, my acid has the concentration of 0.1 moles per cubic decimeter. My base has concentration of 0.1 moles per cubic decimeter. And the base is being added from the burette. So the base is in that thing above our sample, and our sample flask here contains the acid. What we are doing, we are recording the pH of this solution here, the acid solution, all the time. And then we are dropping here the base into this solution. And we are recording the added volume of the base. Now it is sodium hydroxide. And then we have the corresponding pH value. The curve that we get out from it is called pH curve. So let's take a look at a little bit the structure of this pH curve and what is happening over there. So the point 1 is the point when the solution, this here, contains only the acid. The pH of that solution is the pH of the acid. Now, because it is strong acid, the pH will be pretty low. Then we start adding there the base. We add it, and the pH doesn't change that much since there is plenty of that acid. Acid neutralizes the base, and we have more acid there, so the pH will be pretty low. But at some point, when we keep on adding the base, the pH will start to increase rapidly, and at some point it will have, numbers like 12, 13, 14 as a pH value. The equivalence, the pH, increases greatly between 3 to 11. Somewhere there will be a sharp increasement over there. And in the end, we have neutralized all the acid, and we are still adding the base in here. And now with what we are basically doing is that we are measuring the pH of the base. So the pH will be the pH of the base, because there isn't any acid left. It has been completely neutralized. The equivalence point, the point where acid and a base have neutralized each other, is the point between halfway here of this sharpest increasement. And fun fact is that when you are doing neutralization of strong acid with strong base, the equivalence point should always be at pH level 7. Now we can read here what was the used volume of sodium hydroxide. So in this example it is 50 cubic centimeters. We know what is the concentration of the base. It was that 0.1. So the concentration is that 0.1 and the unit is the one above. So now we could solve how many moles we used that base by calculating concentration times volume. And there we have the amount of moles used base. Now we will be using the reaction equation to find out how many moles we used acid and find out the value of interest. Now, please work with exercises. We will be doing some titration when we return back to school in August. Have a good one.